Has been busy with his doctoral program. He investigated integrated CO₂ capture and mineralization, polymer composites, and fiber surface modifications. And during his doctoral journey, Dharmjeet achieved remarkable milestones. He secured an FWO PhD fellowship. He contributed to 12 peer-reviewed journal publications. He received 10 grants and awards, and he delivered 9 talks at international conferences. And here we are today. Last month, Dharmjeet already defended his PhD manuscript in front of the jury, and he tackled a lot of questions during that period. And after that, he submitted his final version of his PhD thesis to the Faculty of Engineering Technology of the University of Leuven on the topic of nacre-inspired synthesis and modification of fillers for better performing polymer composites. Swallow. Now, I don't understand this title, but I hope that after Dharmjeet presented his 45 minutes presentation that we will all know perfectly what that is about. The presentation and what we are doing here today are in partial fulfillment of the requirements for the degree of Doctor of Engineering Technology. So now Dharmjeet will publicly defend his PhD thesis. So may I invite you, Dharmjeet, to start with the presentation after all the technical issues have been revealed, I think. Please beware that we do not hear any sounds from mobile phones. And with that being said, the floor is yours.
Oops. Thank you very much. I hope it's clear. Okay, so I'm going to talk about my PhD, which is nacre-inspired synthesis and modification of fillers for better performing polymer composites. I started 4 years ago under the supervision of Professor Virle van de Hinste and Professor Fredrik Desplanter and Professor Paula Moldernas. So this is the content of my talk today. I'm going to start with the introduction of the project, where I will talk about the research goal, state of the art, and then I will move to the project outcome and findings. And I will talk about the valorization potential of this project, because the Faculty of Industrial Engineering or the Faculty of Engineering Technology requires every research to be valorized. And finally, I will give the general conclusion and the future prospect of this PhD. So to start with the introduction, as I said, I started in November 2020. There are 3 research groups involved in this project. 2 from Campus Bruges and 1 from Leuven. And also, apart from that, I worked with different professors in Leuven and here outside of Belgium at MIT. So many of you may not know even what is nacre. So to start with, the goal of the research and to make you understand what is nacre. Nacre is something called mother of pearl, which is grown inside the seawater through the natural process of CO₂ mineralization. And it is also called mother of pearl because the pearls are grown inside it. So as we can see here. And later I'm going to talk about how fascinating the properties of nacre can be and how we can take inspiration from nacre to make different kind of better performing materials and carbonates. So the overall goal of this research is to develop better performing polymer composites by taking inspiration from nacre and using the constituent material calcium carbonate. So if we look at the nacre at the macro scale, they look like this with a shiny structure. And then if we zoom in a little bit, then we can see that it looks like something with a brick and mortar structure. And if we go further, then we can realize how it is made in nature. So how it is made is that it takes the carbonate ion captured from the environment, from CO₂, and then because of the biomolecules and the biopolymers present in the seawater, the calcium ion gets complexed with those biopolymers, and due to which that the CO2, when the carbonate ion reacts with that, it can have the crystal regulating effect, and then that is how the aragonite layers in nacre, which is a layer by layer structure, is formed. And that is where one inspiration can be taken to develop those different polymorph of calcium carbonate. Calcium carbonate generally has 3 different polymorphs. Aragonite is one of them. Calcite and wetterite are other 2. The most stable is calcite. Aragonite and wetterite are less stable, so therefore it is important to produce them in a way that it stays stable for a longer period of time, and this is one process where it is produced and it stays stable for over a big period of time. So the first inspiration I take in my thesis from nacre is the synthesis process itself. And as I explained, that the polymer which can interact with calcium ion can make a complex and therefore regulate the crystallization of calcium carbonate. So the first inspiration gives me the opportunity to produce carbonates which is synthesized via polymer mediated crystallization. And then I move to the second inspiration, which will be part 2, that is modification, and that is the structure of nacre itself, that how these aragonite platelets are structured inside a nacre layer by layer using a small amount of polymer in between them in a brick and mortar structure. So to summarize all this inspiration, so this is a summary. So the first part takes inspiration 1, the formation of nacre, and that is synthesis of calcium carbonate. And then the second inspiration comes from the structure of nacre, that is the modification part of carbon fiber, and that comes from the structure of nacre. So to move on, how this gets me inspired to do the CO2 capture and mineralization, as I will move in the story, that I will come to capture CO2 and make calcium carbonate using this process. So I want to develop a process which does integrated CO2 capture and mineralization at the same time, controlled crystallization of calcium carbonate. So all three procedures are done in single step, where CO2 can be captured, converted to calcium carbonate, and the properties of calcium carbonate can be tuned. So, and once the calcium carbonate is produced through this way, they will have much more better application potential than already existing applications of calcium carbonate, which are many, like fillers in plastics or paper or coating or in PVC compounds and pipe. So a little bit introduction about the carbon mineralization. Carbon mineralization is a thermodynamically, CO2 mineralization is a thermodynamically downhill process. That means that it is in thermodynamics, it is favorable to go downhill. So many of you may know that or argue that the CO2 is a very stable molecule and it is difficult to react CO2 with anything. In this case, when CO2 is converted to carbonate, it is actually more stable form. So it is easier to do that process than converting CO2 or reducing it to some fuel. So this is a promising way to convert CO2 into carbonate. So there are two different types of carbonation, let's say. Direct carbonation, which is one step, and then indirect carbonation, which is two step. In direct carbonation, in one step, mineral or aqueous solution, which contains the calcium, is directly reacted with CO2 to form calcium carbonate. And in the indirect path, which is two or more steps, first the calcium ion is extracted from the mineral, and then it is reacted with the CO2 to form calcium carbonate. So these minerals and aqueous can be sourced from different places. So here I'm showing the wollastonite, which has 51% calcium oxide, or the steel slag, which has 35% calcium oxide, or the water purification brine. A lot of water purification is going around the world, which produces a lot of brine. The desalination concentrate, it has a significant amount of calcium, and also it can be also magnesium, not only calcium, but magnesium can also be reacted in a similar way to produce magnesium carbonate. So potentially, if we look at just the concentration of magnesium and calcium in seawater, it is significant concentration, 400 ppm of calcium and around 1200 or 1300 ppm of magnesium. So potentially 1 ton CO2 can be captured in 370 ton of seawater, producing 2.1 ton of carbonates, which will have around 80% magnesium carbonate and 19% calcium carbonate. So from here to move on, after giving the little bit of introduction, I will move to my real research and the outcome. So with this idea of making one-step CO2 capture mineralization integrated with the carbonate crystallization, I started looking up at the different research questions which are following, like if the process is feasible, if the method can be green, if we can use less toxic chemicals, ambient condition, not high temperature, high pressure, and if the process is efficient. That means that if we can produce not a lot of waste out of it or the residue which we don't need, and if at the end, if the process overall is economically interesting, because without economic interest, if we produce such material, there is no use of such thing. So at the start of every I would say a research question, I have divided them in several smaller questions, and then I will try to answer those questions on the way. So how do amine-based CO2 absorption promoters facilitate the integrated CO2 capture and mineralization, and if the surfactant and polymer combination can be used to tune the properties of calcium carbonate? In that sense, I started looking at this process where I used amine-based CO2 absorption promoter in an integrated CO2 capture and mineralization process. And the variables in that case I used was CO2 absorption promoter, their concentration, their combination, and then the CO2 bubbling time to understand how much time do we need to react this CO2 with the calcium ion to produce the calcium carbonate. And also, as I said, using the surfactant with the polymer to produce different crystals, which is normally used in the reaction system where there are two reactant systems are used in a precipitation reaction, like calcium chloride and sodium carbonate, just to react in the presence of surfactant and polymer to make different types of calcium carbonate. So then I also analyzed the sample with different analytical techniques, which is SEM, scanning electron microscopy, FTIR, XRD, and TGA. I'm not going to go in the technicality of all this process, but I will show some SEM images later on to show how it looks like, the produced material. So now if we talk about how this CO2 gets reacted with amine. So this is a general structure of amine, which I'm taking an example of triethanolamine. CO2 is a molecule which reacts with TEA and in the presence of water and produces protonated amine and a bicarbonate. Bicarbonate, depending on the pH of the solution, can be in equilibrium with the carbonate ion, and carbonate in the presence of calcium can be reacted to produce this solid calcium carbonate minerals, which is solid product and can be removed from the reaction system and can be stored or used for a very long time without losing the stability unless we have interaction with the acid. So I started looking at this process, and then I found that the efficient time for this reaction is within 5 minutes. Depending on the concentration and the combination of the promoter, we can reach the maximum conversion within 5 minutes. But the particles, when they were produced just with the absorption promoter, they look like, let's say, cubical, or in more technical term, rhombohedral. They were the particles which is already in the nature, and we have more than 4% of the earth crust is made of calcium carbonate, so we have enough of calcium carbonate in the calcite form. So we need a different form of calcium carbonate which has more application potential. Therefore, I was looking at modifying the crystal properties of the same material to produce different polymorph. And then I took the inspiration from Nacre, let's say, and then I used this polymer PVP and surfactant STS, which can interact and form a missile. And then in that case, the calcium can form a complex with these particles, and therefore it can tune the crystallization of calcium carbonate. So as we can see, after the use of the surfactant and the polymer combination, the properties of the calcium carbonate were tuned, but they were still calcite in nature, and there were several challenges which I'm going to talk next. So the highlights and the main findings of this part of the research was that simultaneous CO2 capture and mineralization at the ambient condition and pressures is possible. Around 53% calcium can get converted to calcium carbonate at ambient conditions in the room temperature. The method has also the possibility of the solvent recovery and reuse. The particles property can be tuned using this polymer-mediated crystallization, taking the inspiration from Necker. But there are some limitations. The first one is that amine-based CO₂ absorption promoter can be toxic and require under fume hood operation. And also, there was the conversion was only 53%, so it was not sufficient. And there was excessive foaming due to SDS, which we all can relate to the foaming in the beer. So there were a lot of foam, and it created issues with the reaction system. So the next question was, how about moving to another kind of absorption promoter, which is more environmentally friendly, let's say amino acid-based absorption promoter, and exploring how different water-soluble polymer can influence the properties of the calcium carbonate, which will not have this problem of producing lots of foam. So in that case, I started using arginine, which has 2 amino groups, and it has the more possibility of reacting with CO₂ due to that. And then I started looking at different polymers which can form complex with the calcium. So it interacts with the calcium and forms a complex, and those polymers can be polydopamine, polyvinyl alcohol, or polyethylene glycol, or polypropylene glycol. So I investigated all of them one by one at different concentrations to investigate how it will affect the properties of the calcium carbonate, and also the different combination of the calcium concentration and the CO₂ absorption promoter concentration to find out what would be a good ratio to have the optimal conversion. So as we can see here, using just polymer with the absorption promoter produced calcium carbonate with different size and shape, and spherical, and also very well dispersed, which can be advantageous in many ways. And then the main findings of this part of the research was that the greener method with no toxic chemical used and at the ambient condition can still produce veterite particle of calcium carbonate, which is spherical and porous and stays stable for a longer period of time. A maximum of 98% conversion from calcium to calcium carbonate can be achieved within 5 minutes compared to the previous method, which was 56%. That is the maximum. And then at the practical optimized condition, a 92% conversion was achieved compared to 53% in the previous one. And also the high concentration of calcium was used in this case. That means that more amount of calcium carbonate can be produced in a smaller reactor. That is very useful to produce bigger amount, because that will help to increase the efficiency or the yield of the reaction, not in the sense that we are having more conversion, but we are having bigger amount of calcium carbonate in a smaller volume of reactor. And this method also has the possibility of recovering the CO₂ absorption promoter and can be used several times. And then I will move to how the operating parameters, such as reagents concentration, CO₂ injection rate, or the reaction temperature affect the process and the properties of the calcium carbonate. Before that, I will take just a sip. So in this case, I studied different amino acid as well, because this gave me opportunity to try different types of amino acid, different types of different calcium concentration, flow rate, crystal growth modifier, all the combinations to investigate how it will affect the calcium carbonate and learn more about how to control the crystallization of calcium carbonate. So first I started with the glycine concentration. If we change the glycine concentration, keeping the concentration of calcium fixed, the conversion starts increasing with the molar concentration of glycine, and at a certain point it reaches the maximum, and then it doesn't increase anymore. And in the case when we increase the calcium concentration and keep the glycine concentration fixed, it also has the similar effect, and it increases initially, or it stays the highest, and then start decreasing because there isn't enough supply of carbonate ion. And then the CO₂ injection rate does not have, let's say, too much, or let's say significant effect on the extent of calcium conversion to calcium carbonate, but it certainly affects the properties of the calcium carbonate, which I'm going to talk next. So in this case, I also investigated different types of biopolymers, which is found in the nature. to understand if they can have effect on the calcium carbonate crystallization. And those were gelatin, xanthan gum, pectin, and casein. And these all polymer have the possibility to interact with calcium ion. So therefore, they can change the nature of nucleation and crystal growth of calcium carbonate. So the main findings from this part of the research was that the reagent concentration, the effect of reagent concentration was that the glycine to calcium ratio has to be more than 2.3:1 to optimally convert all the calcium present in the reaction system to calcium carbonate. The molar concentration of amino acid has to be higher than the calcium to have the production of this vetrite calcium carbonate, which is the spherical one. And CO₂ injection rate, as I said, it does not affect too much the conversion, but it affects the polymorph. It does not affect the conversion, and also it produces the calcium carbonate in the same polymorph vetrite. But the higher CO₂ injection rate produces a smaller particle because the reaction becomes faster. And the reaction temperature was also investigated. At the reaction temperature of 50 and 70, it resulted in an increased conversion, but of course the higher temperature increases the kinetics of the reaction. That's why the conversion can be increased. And the produced particles at 30 and 50 degrees were a mixture of calcite and vetrite, but at 70 degrees it was mostly calcite. And with the use of the casein, which is a protein found in milk, it can also interact with calcium and form a complex with calcium, and that has the stabilizing effect on the production of vetrite. And the amount of calcite produced with the use of casein was reducing with the increasing concentration of casein. So now I will move to how could we use this CO₂ mineralized calcium carbonate to produce better performing polymer composites. So I used this process to make so I use this already produced calcium carbonate in bulk to produce polymer granules. So first, the PLA granules, sorry, it should be PP. The PP was mixed with flex straw and calcium carbonate, and then it was produced through the extrusion, and it was mixed together to produce these kind of pellets. So this is the process which is used, but in reality, I use this twin screw extruder in Leuven, which is the mini extruder, and it was used to mix all these PP and the calcium carbonate and the flex straw to produce these kind of granules. And from using these granules, I used the injection molding process, which looks like this, where you pour the granules, hit it, and then you push it through a mold and cool down to produce a sample. And in that process, but in reality, I use this mini injection molding machine, which produces a smaller version of this dumbbell-shaped mechanical property testing specimens. So, and then after that, the mechanical properties were tested, and I found out that when I use only calcium carbonate with the PP, the elastic modulus and the strength both tends to decrease. But when I use it in the combination with the flex fiber, normally flex fiber is supposed to increase the elastic modulus and strength, and when the calcium carbonate at 10% and 20% weight percent, they were both used in the combination, the increasing trend in the elastic modulus and the tensile strength was maintained, and the elongation at break increased when the calcium carbonate is used because of their spherical nature and the smaller size. So the main finding from this part of the research was that the combined reinforcement of flex and calcium carbonate maintains the increasing trend in the elastic modulus for both 10 and 20% flex composites. The displacement at break value increased with the use of calcium carbonate and when it was only purely with the flex at 10% and 28%. The hybrid reinforcement of flex and calcium carbonate was found advantageous in enhancement of mechanical properties overall. So for the thermal property, there wasn't significant change in the thermal property of the composite, even with the high filler content. And the sound absorption coefficient was also measured of these composites, and with the incorporation of the calcium carbonate, the frequency range of the maximum absorption was narrowed, and the sound absorption coefficient increased. So now I will move to the second part, which is the second inspiration from Naker, which is the the layered structure and the modification of filler, which is carbon fiber in this case. Carbon fiber is generally inert and smooth, so it has limited mechanical, let's say, interlocking with the polymer when it is used with the polymer composite. So if we increase the roughness, it can have advantages in terms of better mechanical interlocking. So I was trying to put a layer by layer structure to make a carbon fiber more rougher, let's say, in that sense. And then I used first the carbon fiber. It was desized, and then a polymer called polydopamine was deposited on the surface, and then it was interacted with calcium to have the calcium ion get deposited on the polydopamine deposited carbon fiber, and then finally this was interacted with the carbonate ion to produce carbon fiber coated with polydopamine and calcium carbonate. And then this process was repeated several times to produce layer by layer structure. And if in reality, if we see the SEM scanning electron microscopy images of this carbon fiber, we can see that this is the desized carbon fiber, and then this polymer polydopamine is deposited on this carbon fiber, which has the, as we can see clearly that there is some layer of polymer on it, and then finally when the calcium carbonate is deposited on the carbon fiber surface. And then there was lots of optimization done in the process to have the calcium carbonate deposited properly. First was to the washing step after the polydopamine deposition, and also after the reaction with the calcium carbonate or deposition of the calcium carbonate. Because if the washing is not done properly, there will be lots of uninteracted polydopamine on the surface, which will capture lots of calcium on a particular location in the carbon fiber, and that will interact with carbonate to have big chunks of calcium carbonate deposited on a particular location on carbon fiber. So ultrasonication was used, which removed the unattached or uninteracted polydopamine and calcium both in the reaction system. So, and then again, it was the same procedure used here, and polypropylene with modified carbon fiber was mixed together using a mini extruder, and then it was produced. The mechanical testing specimen, like dumbbell-shaped specimen, was produced through the similar way as it was done in the previous PP, flex, and calcium carbonate composites. And then finally, the mechanical properties were tested. And in that case, it was found that the polydopamine-coated carbon fiber had the maximum strength and modulus both, and also as the calcium carbonate deposition or the layer of calcium carbonate deposition increased, the mechanical properties in terms of tensile strength and tensile modulus started decreasing. But we have to understand here that the weight of the carbon fiber was kept constant, and as we increase the layer of calcium carbonate on the carbon fiber, the amount of calcium carbonate, which is generally denser compared to carbon fiber, is increasing. Therefore, the effective amount of calcium, the carbon fiber in the composite is decreasing. Therefore, the mechanical properties are expected to decrease. Therefore, in future research, it is recommended to keep the carbon fiber amount constant while adding more calcium carbonate. So main highlights and the findings of this part of the research was that the calcium carbonate layer from 1, 2, and 3 cycles significantly increased the fiber diameter, which can be disadvantageous. And the washing of the sample after the PDA coating and also the interaction with the calcium carbonate is found to be very crucial, so it has to be done properly. The calcium carbonate deposition on the wet PDA coated, so the drying also has significant effect. If the drying is not done, then there will be lots of chunk of calcium carbonate. The tensile strength and the tensile modulus were maximum for the PDA coated carbon fiber composites, and the modification of carbon fiber with calcium carbonate was found to be the most advantageous in terms of increasing the toughness of the carbon fiber composites. So that takes me to the valorization potential of this whole PhD, or mainly about the CO2 mineralization part. So in this case, I conducted a business case study from taking the example of flue gas from ArcelorMittal cement. low battery. So I conducted a business case study, taking the example of flue gas coming from ArcelorMittal steel plant in Ghent. So first I will look at the general calcium carbonate market in US and in Europe. So if we look at the calcium carbonate market, both the ground calcium carbonate and the precipitated calcium carbonate, it is expected to grow significantly in the coming years from 2024 to 2030. It is expected to grow at 6.6%. And if we look at the segmented calcium carbonate market in Europe by application potential, there is a lot of application in terms of industrial fillers, water treatment, and this other chemical production. So there is a huge market potential in general in the calcium carbonate market. So now if we look at the case study where this is the example, this is the photo of the real ArcelorMittal in Ghent site where they produce a lot of steel, and it was considered fourth largest polluter in Europe overall in many terms. So it has production of flue gas around 600 tons per hour, and which consists of 37.3% CO2 and 55.2% nitrogen and small amount of other gases. So I take an example from my own research at the lab scale and try to scale it up to use the flue gas produced from the ArcelorMittal plant. So in that case, I see that we can use a significant amount of CO2 coming from the steel making process to produce the calcium carbonate. So then this is the process which was estimated or suggested, where the water with the calcium chloride solution comes in the reactor. The flue gas is sent to the reactor, and then the product is separated and dried to produce dry calcium carbonate. And then also the residual CO2 gas go to the another reactor where there is direct aqueous mineralization of steel slag is done, because in steel production, while they produce flue gas, they also produce a lot of steel slag which has significant amount of calcium concentration. Therefore, this steel slag can be mineralized to have this slag mixed with calcium carbonate, which can also have a good application in many terms. So the operating cost was calculated based on earlier research done in this field, and some research were done by me. So the calcium, all the cost of operating expenditure was calculated to be around 63 million per year, and then the capital expenditure to make such plant was estimated to be around 10 million. And then if we add this the depreciation factor of this, the total cost of the product for a year becomes 64 million euro. So, and this will produce 118 kilotons of spherical calcium carbonate particles, 250 kilotons of mineralized slag, and that will utilize around 63 kilotons of CO2. So these are the three main products which can be sold out of this business plan, which is the calcium carbonate particles, mineralized slag, and the CO2 which has been utilized. So if we look at the market of all three one by one, so the global carbon credit market is significantly increasing, and the EU regulations are making it even more interesting to sell the carbon credit. And the price is currently estimated to be around 75 euro per ton of CO2 captured. It is going to increase in the coming year as the regulation becomes more stricter. And if we look at the global steel slag market, there is a huge potential in the fertilizer sector. So if we can remove the unwanted hazardous material from the slag, then it can have significant application potential in terms of fertilizers. And for the mineralized spherical calcium carbonate, there can be several applications it has been diversified in the business plan so that there are many applications. So first application is suggested to be used as fillers in filter production, water purification filter production. It can be used as fillers because they are spherical in nature, smaller in size, in automotive parts, which is made of polymer composites, and also as fillers in PU foams, because it will improve the mechanical properties and the sound absorption and the acoustic properties. So if we look at this pricing, so by taking the example of these three markets and selling these products in those markets, a total of revenue can be created around 79 or let's say 80 million, which will give a profit because the cost of the product was around 64 million per year. It will give a profit of around 15 million per year. So that brings me to the final conclusion and the future prospect of this research. So the main takeaway from this research is that the CO₂ mineralization, the integrated CO₂ capture and mineralization with the carbonate properties control is possible at ambient condition, at room temperature, and at normal pressure. The amount of amino acid used to the ratio of the calcium has to be more than 2.3:1 to produce or to convert optimally the calcium to calcium carbonate. The use of the surfactant, normally which is used in the two reactant precipitation reaction system, is not useful in this case because when you bubble CO₂, it will produce a lot of foam and a lot of product will be lost during that process. The polymer addition of water-soluble polymer, which can interact with the calcium, has the potential to tune the calcium carbonate properties. The scale-up studies for the outlook of this part, the scale-up studies should be conducted to use the solid minerals to produce calcium carbonate through this method. So pilot studies and the studies where the slab scale is replicated in a bigger level to produce higher amount of calcium carbonate should be done. The other application of this calcium carbonate, in this case I use them to produce this polymer composites, but there could be several applications and the other applications should be explored. And for the other part, the surface modification or the modification of fillers inspired from Naker, there are so many potential applications to produce different types of layered composites for several applications, starting from electromagnetic shielding to different thermal insulation and many more. But in this case, what I found is the surface roughness of carbon fiber and the diameter increases with the calcium carbonate deposition, which is disadvantageous in some sense. So the reaction needs to be tuned to produce smaller calcium carbonate particles or a smaller layer to control the diameter of the carbon fiber. The strength and the modulus, which is still higher than the pure PP, but starts decreasing with the amount of calcium carbonate when they are added. So the research should be conducted with the same amount of carbon fiber on each and every polymer composites to have a baseline which is comparable. And in the future research, which I already mentioned during the conclusion, but the studies accounting for the same amount of carbon fiber or considering the density change in the carbon fiber should be conducted. The single fiber-based composite testing, that means that how the single fiber has the interaction with the polymer should be investigated, and then we will have the potential to more precisely control the mechanical properties or the interfacial properties between polymer and carbon fiber. And the modification of fiber can be extended to a wide range of fibers, from natural fiber to different fiber like steel fiber, and the application can be extended to several other fields. For example, in the electromagnetic shielding, we need a conductive and magnetic fibers to be placed inside a polymer composite, and in this case, carbon fiber which is conductive can be deposited with the magnetic iron particles, and then it will have better performance. So with this, I would like to thank all of you for your attention, and I'm happy to answer any question you may have. What would you like? Ah.
Okay, thank you, Mr. Madhav, for this presentation. We now move to the second part, and that's the questioning by the members of the examination committee, and that gives me also the opportunity to present to you the jury members. Yeah. This jury is composed of several people, of which, of course, the supervisors. We have Professor Veerle van de Ginste, who is the main supervisor from the Department of Materials Engineering. Then we have two co-supervisors, Professor Frederik de Splentere and Professor Paula Moldenaars, also from Materials Engineering. In this jury, we also have a secretary, which is a big task. This is Professor Arne Mignon, also from Materials Engineering. As additional member, we have Professor David Seveno from Materials Engineering. And then we have two external members, Dr. Paul Lombaert from Beaulieu International Group and Professor Ron Zevenhoven from Abo Academy University from Turku in Finland. To the latter two of you, thank you very much for your engagement in this jury, and we are very happy that you could be here live in person today. Well, as under normal circumstances, we start with the person coming from the furthest, which brings me to you, Professor Zevenhoven.
Yes, this will work. Yeah, this works fine. Well, Dharmjeet, a lot of work done, a big book produced, a lot of facts, a handful of quite solid publications in good journals, quite a few other publications, and I remember in December, could you please split up the list of publications in actually what you put in the thesis here. So one thing I could maybe start with is to congratulate you in what was done, pass it also on to your relatives and family. This was useful and worldwide, and it's I think that's also one reason why I decided to come here, because I think it was a bit of a token of appreciation, and also to the university for having me in as part of this team here. So good presentation as well here to wrap it up. Also, I'm impressed and pleased to see how the thesis developed after December. You were asked and, well, forced maybe to make some changes and to add a few things, and you even though these didn't come the strongest for me, you still made quite some modifications that I saw relate to what I have been commenting. So that's also appreciated, so that we actually have a thesis that's different from the one that we thought needs to be a bit different. So, but one or two things can still be discussed here. So, of course, my biggest concern in the beginning was not what you did, but what you wrote as based on what you did. Is you said that now it's formulated much cleaner now at the end about producing bigger amounts. I mean, sometimes you can say chemical engineering is about the physics and the math that you need to do chemistry on a large scale. Not about the chemistry, that's what the chemists do, but how can you do chemistry in a large scale. What's the math and physics there? And I thought in December or November there were a bit of untechnical phrases there about that it cannot be done, and that's not the purpose. You made one good point there. Maybe it's not needed. I mean, if you need a kilo, why make a process that can make 100 kilo in a certain amount of time? But still there is a little bit apprehension here, if I say so, about taking this to a larger scale. So besides that, you say, well, maybe there's no client, so why would I make 100 kilo if 10 kilo is enough? What is your biggest concern here? Why there are some limitations here? Of course, you can be arrogant and say, I can change the world with this, what I produce, and that should be big time and big factories. But what do you still see as the biggest technical challenge to do this on a larger scale?
I think the life cycle assessment should be done to first assess that if it is really CO2 neutral, because it will require lots of energy, and as you said during your mid-century seminar, that it depends where the electricity is coming from. So I don't know if we are doing it using completely, let's say, solar or CO2 neutral energy, then the process is good, and also the reagents where they are coming from. If the calcium chloride is used as a reagent which is not coming from a CO2 neutral source, then it will have certain impact on the overall CO2. So to answer your question, like what is the biggest limitation is that there are so many techniques I mentioned in this to make this whole closed loop process, and each of them are independently developed by different researchers. So I think there has to be a combination of force, as you are doing now. Also, the electrodialysis is combined with the mineralization, so now it is coming together. But some people work completely on electrodialysis, some people work on mineralization. So we need to have a good collaboration to have this process completely closed loop, where we will have no energy output, or let's say no CO2 neutral or CO2 producing energy input in our reaction system. So I think the closing of the loop needs investigation on the whole system, the LCO of the whole system, and not rather just a smaller part. So in that sense, I think that can help producing calcium carbonate at a market scale, which can be CO2 neutral and have a good market potential.
Yeah, I think you have a good point there, because you may have different steps in the process, and each may have a company specialized in these, yeah. But each of them maybe wants to offer a package and not just one technology, not just a membrane or not yeah. just a reactor or something like that. Then again, about this sustainability and life cycle assessment and probably staying as close to nature as possible. In a way, somebody asked me once, what is actually now sustainability? Well, it means that if you have 1 year annual cycle around Earth, that we have the same amount of oil and gas and coal in the ground as now. That's what I think is sustainability. Take one cycle of a year, for example, but there are many discussions and the definition of sustainability. But you see more and more, like also you've been doing, looking at nature. What does nature do? What does nature make? Should we follow the same rules? We see things like fractals and stuff like that, describing the physics of nature. But in the beginning, you write the nacre material, about 95% carbonate and 5% biopolymers. Yep. Were you forced to stick with that? Did you see that if you go to completely different ratios that it actually doesn't really work? Because probably nature has figured out in millions or maybe billions of years that 95-5 is a good ratio. Did you see that also in the lab?
Yes, in the sense that, you know, when you use too much polymer as an additive to control the crystallization, it will have certain negative impact. It can form the chunk, it can form this already a missile or a chunk of calcium carbonate fixed with the calcium carbonate. So we need to use really low concentration. We have to assume that how low concentration of these biopolymers are in the seawater that can still control the crystallization of calcium carbonate. So 1 milligram per liter or 1 gram per liter, something like this, is already a very high concentration, and it can have significant impact on the crystallization already. So we have to tune and go really from the small amount to the big amount to see where we find the optimum concentration which will have good properties on calcium carbonate.
Yeah, that makes sense. And of course, in nature, it varies from place to place, these ratios of chemicals that are needed. And then it may grow or may not grow. If you would, for example, contaminate with a lot of magnesium, you will get very bad shell-type materials, and has been shown. I would actually want to wrap it up. If you would maybe go to your slide number 22, it's just a question that arises, and after that I can pass it to my colleagues here. The reaction temperature. We are labbing or doing a lot of lab work on phosphogypsum, and we try to make something that paper making or those types of industries can use. So we want to go for aragonite, and for that usually we go a bit over 40, 45. Depend a bit on contaminants and stuff. But now I wonder, you have here a mixture of calcite and vaterite. The question is, why didn't you see aragonite? That simple thing.
So normally, it is expected that when you go higher temperature, it would be aragonite. But in this case, maybe there is an effect of glycine. So glycine already can interact with calcium and therefore have the effect. So I also found several other research where there is production of calcite at higher temperature. So normally calcite and aragonite are favored at higher temperature, and vaterite can be produced at lower temperature. In this case, we found that it was calcite at this reaction condition. So maybe if we don't use glycine and use another CO2 absorption promoter, we may have the formation of aragonite. Actually, we produced aragonite at some reaction condition, which I did not mention in my thesis, but using ultrasonication produces aragonite with the reaction system where it was with the polymer and surfactant in the first one.
Yeah, well, in general, we start to conclude that if you don't have something that's clean or pure or clean enough, then you won't get your aragonite anymore. So apparently that happens here. So you must, if it becomes too complex, then it's end of the story. Okay. But I think I will leave it there. Thank you very much.
Thank you.
Thank you, Professor Zevenhoven. Then we move to Dr. Pollombert.
Thank you, first of all, Dharmjeet, for your hard work during the last 4 years, and of course also for this nice lecture today. Still, I have a couple of questions left for you. I was this afternoon kindly reminded by Professor de Splentre on the fact that in 2020 I stated that as industry we are continuously digging up whole mountains of calcium carbonate from nature, which is true. So he was right in saying that. So if you look now with the process that you have found, look 20, 30 years ahead from now, could we then stop digging?
If we can produce it as cheaper as you can get it by digging, so of course then it would stop the digging. If we can sell you at the same price you get it with the digging. So to go there, it needs some research still at the pilot scale and the more scale, but I think it is a possibility that you won't have to dig it up if we can make this process work at a bigger scale.
That would be nice, but of course you need two sources for that. On one hand, you need the calcium source, as you've explained in one of your first slides, and you need CO2. I presume for a second that CO2 is plenty available, but what about the calcium source? Do you find enough of that one?
So I presented in the start that there could be several sources of calcium. So there is another. So we have to dig again.
Yeah, but that's digging again. Let's forget about that. So,
but then we have the,
let's say, industrial waste. Is there enough calcium available somewhere?
So also in the steel slag. So there is 35% calcium there. So there is one source, and then also the water purification brine. If not this, then we have a lot of seawater. Seawater already has a concentration of 400 ppm, which is 0.05 molar. So seawater can be concentrated to make higher concentration of calcium, and then we have the rich source of calcium and also the CO2. So that is a possibility.
Okay, good. Then the next question, if I may. You reasoned in your last chapter, before concluding, of course, about the business case, which indeed is more of a hypothetical reasoning, of course, I know. But suppose now that the whole process that you're developing is successful and that also you find the right sources. But between starting such a factory and really becoming commercially a viable thing, what are the next steps that need to be taken there, apart from the LCA analysis?
Yeah, so I think the first one would be to patent it, but it's not possible because I already presented to public. So, the second is that it is good for the humanity that I disclose this process and anybody can use it. In that case, it needs several process optimization, which is now based on hypothetical situation or hypothetical assumption. So it has to be done at pilot scale. The glycine has to be used as a CO2 absorption promoter. It has to be taken back, regenerated, reused again, and see that how much we are losing and how much we can reuse it. And then if everything works out, then also if the calcium carbonate, as we assume that it will be produced, is getting produced in the same way.
Yeah, that's all very much on the technical side. Yeah. But what about the business side of things? How are you going to be able to sell it and to convince the market that this is now the best stuff in the world to be used?
Yeah, the first thing is the sustainability, because I'm using CO2 to produce it, and I think everybody in the EU and all over the world, except few countries, that they are forced to be more sustainable, more greener. So if I am saying to my customer that, okay, you are getting this produced from CO2 and you can use it to market your company as a green company or sustainable company, then of course I get some attention from them for sure. And the other thing is that the better properties. So those who are getting it from digging the mountains can get, if they can get better property of same material, then I think they will of course like this material. Yeah. So these 2 points I think is something to start with, and of course there would be many more, like better customer handling and all these things.
For sure, don't underestimate it. Yeah.
Yeah.
Okay, thanks a lot.
Thank you, Dr. Lombaert. We move on to Professor Seveno.
Yeah. So thank you, Dharmjeet, for your presentation. Again, it clarifies a few things, so it means I have new questions.
Yeah.
Just a couple of new questions. Maybe you can go back to slide number 7. It's a very maybe naive question to begin with, but next one, yeah. It's about, so it should be, yeah, this one exactly. So if I understood correctly, potentially you could use seawater as a source of raw materials, but you will produce more magnesium carbonate than calcium carbonate.
Yeah.
So shouldn't we more focus on magnesium carbonate as something to valorize?
Yeah.
Or is it a useless material and then we should indeed focus on calcium carbonate?
No, the problem with the magnesium is that it is less reactive. So doing the research with magnesium it does not give the same kind of conversion. It takes a lot of time. It also requires many times higher temperature. The reaction kinetics to react CO2 with magnesium is very slow compared to calcium. So many people focus on calcium, but some people, like Professor Zevenhoven, also works with magnesium. We tried with magnesium. It takes a lot of time. It is very slow, and it doesn't work quite well.
So we need a second Dharmjeet to focus on magnesium carbonate to redo a PhD.
And also the price of magnesium carbonate is comparatively super high if we compare it with the calcium carbonate. So if we can, it needs more time and energy to produce, but the price is around 800 euro per ton or something like that.
Maybe you can jump to slide 24 just to illustrate or support my question. So now you are mixing polypropylene granules together with calcium carbonate particles. Are they compatible?
Calcium carbonate with PP?
Yeah.
That I did not investigate by the single, like how the wetting works, but there is significant amount of research on using calcium carbonate in polypropylene, and it improves the mechanical properties, even when it is used as just as simple filler without any plex.
And if you would need to treat the calcium carbonate particles to make them more compatible, I mean, very broad language here, but compatible with PP or whatever polymer, how would you treat these particles? Can you treat these particles to make them surface?
I saw some
different?
research where they can do it. So I think, in my opinion, the only reason to treat it would be to avoid the agglomeration of calcium carbonate, and that is done with stearic acid or oleic acid, something like this, with this kind of surfactant.
My question is more about how would you do that? Which techniques or technologies would you use to treat small particles? Because we know how to surface treat flat surfaces, monoliths. That's quite clear. It can be through plasma or wet chemistry. There are multiple methods. But I was warning about these small particles or these granules or the short carbon fibers. How can we treat these things at a large scale, not at a large scale? Is there a way?
Yeah, it must be wet chemistry. It has to be mixed with the concentration, or it can be also during the processing. So I saw some research where they use stearic acid granules during the processing in the compounding process. Just add as a solid, and it will mix, and it will improve the compatibility so it is used as a compatibilizer.
Okay, so there is maybe a room to move away from wet chemistry and find other ways to treat particles. Another maybe a small technical question about the particle size distribution. I think you said during your presentation that you were able to get quite well control about the size distribution of your particles. Does that mean that you can really have a monodisperse distribution from the nanoscale to the, millimeter scale or centimeter scale?
Yeah, so it is possible to control the particle size. So if we just take the example of CO₂ injection rate, as the rate of the CO₂ injection increases, the particle becomes smaller, and most of the particle becomes smaller, not like only some of them. Also, the polymer, depending on what kind of polymer I'm using, and like as a additive to improve or to control the crystallization of calcium carbonate. So some polymer makes it bigger depending on how they interact with calcium, and some they make it smaller. So it has to be investigated case-to-case scenario, and if we need smaller, I have the recipe which I can do that, and then it will make it smaller.
Okay, good. And last question, very broad and open question, but throughout your 4-year PhD period, you focus on experimental work. There is no word about simulation of whatever kind. And I was naively wondering if you would, if there's a need to do simulation, and if you would have the skill to do simulation, maybe you have, what types of simulation would you do? Would you model the way to construct a new plant? Or would you go to the mechanism between, the Ca cation and the polymers at the nanoscale? Yeah, what would you like to do if you would have time?
Yeah. Initially, I planned to do some modeling with the molecular simulation to understand how this polymer and calcium interact, so that I have a larger number of, I don't have to do many experiments, and I would already remove some experiments by knowing that which polymer is interacting faster and more strongly with this calcium and forming a complex, so that those which are not interacting enough, I remove them from my experimental plan. But I couldn't do that, those molecular simulations. So I would certainly like to do that, because there are lots of water-soluble polymer in the nature or the artificially made, which can have this kind of effect. And if we have a system which quickly can tell us that how much interaction is there, that will help exclude many experiments.
Yeah, thank you very much.
Thank you, Professor Sevino. And then we move to Professor Mignon.
Thank you, Dharmjeet. Also for a very nice presentation, also for the booklet. I was surprised that you were able to put all of the work in only 200 pages. So As being the last of the jury members, I have the privilege that half of my questions have already been asked. So I still have a few questions left. I want to come back to maybe the question that Professor Siveno was asking, the last question, with the modeling. Because you have been working with different polymers, synthetic ones like, synthetic ones like polypropylene, but also with biopolymers. With the biopolymers, would you be able to predict with the biopolymers, because they're huge molecules, the modeling of those is very difficult, I would presume. Would you be able to predict their interaction and how they would cause a change in the morphology or in the properties of your calcium carbonate?
Yeah, how it will affect the morphology, I don't think it can be predicted. But this interaction, the interaction force between the bonds, I think that can be predicted with the molecular simulation. So I think that's possible.
The fact that you're using these biopolymers, if you use them as partially as fillers, will they not have negative effects on the longer term? Because some of these will, like for example the gelatin or others, will attract bacteria. Will that not cause any problems?
No, I'm not using them as fillers. I'm just using them to modify the crystallization of calcium carbonate.
At the starting process, at the beginning of the process.
Yeah.
I had also a bit of a similar question with the magnesium carbonate. As you said, it's a difficult process to make it. It's a longer period of time, more costly. Taking those two facts aside, do they have the same properties? If you make magnesium carbonate versus calcium carbonate, do they have similar applications in the end? Do they have similar end properties?
No, actually they have even better application potential. Today it was presented that if you produce magnesium carbonate, it can be used as energy storage material. So you can store energy and then release the energy and then store again. So it has better application potential, better price, everything good, but the reaction is slow to produce it.
Yeah, okay. I had a small question also still at the last chapter, so in your valorization potential. You were showing the potential that calcium carbonate has also in Europe. Oh, previous slide. Yeah, no, that one, yes. I was wondering the part with the citric acid production. Why is calcium carbonate used there? Do you have any idea?
I had idea, but I forgot about it. I knew how it is done. I think it is one of the reagents to produce citric acid. But I currently don't know the reaction by heart.
I also don't know, so that's why my question, I was very curious about it. I have a general question. You have done quite a lot of work, right? Over this more than 4 years. Your most challenging part of your entire PhD, what could it be?
I think the first year of my PhD where I was using surfactant, it was creating lots of foam, I was still wanted to make it a successful way because I read in the literature that it is very simple to do it, just calcium chloride and sodium carbonate, you mix it in the presence of surfactant and polymer, it gives different types of particle, but when I use it with the CO₂ injection, it produces a lot of foam, and then it was struggling, and I did not want to give up on that. So I was trying to control in a different way, and at the end, it was one of the reasons that it has low efficiency and many problems with that process. But then I moved on to find better ways. Yeah, that was the most challenging.
I think with what we have seen here, that you have proven that you haven't given up in those years. So, thank you.
Thank you, Professor Mignon. The supervisors have indicated to me that they did not want to ask questions, but perhaps they changed their minds? No? Okay. Well then, ladies and gentlemen, since this is a public defense, also the audience has the possibility to ask some questions. Do you have any questions for the PhD candidate? If not, it means that everything is clear and Dharmjeet will have the possibility to ask questions to you. No one? Really? Not? Okay, well, in that case, the jury will retire for deliberation and we will be back in a few minutes.
To those watching online, it will be back in around 15.
Ladies and gentlemen, dear colleagues, I have the pleasure to announce you the results of the deliberation of the examination committee. Dharmjeet Madhav has submitted to the Faculty of Engineering Technology of KU Leuven a PhD thesis on the topic of nacre-inspired synthesis and modification of fillers for better performing polymer composites in partial fulfillment of the requirements for the degree of Doctor of Engineering Technology, and he has publicly defended his thesis to the examination committee. The examination committee has determined on February the 11th, 2025, that all legal requirements and all requirements of the KU Leuven regulations with regard to the doctoral exam have been fulfilled. Therefore, on behalf of the rector of KU Leuven, I confer upon Dharmjeet Madhav the degree of Doctor of Engineering Technology. Congratulations. Dr. Madhav, by obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALIA European Code of Conduct. That is, reliability, honesty, respect, and accountability. The session is closed.
I have something to write. It's okay. No, it's okay. It's okay. There we go. Just need your signature here. There we go. And then I have more official document for you. Congratulations.
I think now your promoter wants to.
Just a brief word. Yeah, so the chair already introduced Dharmjeet, but I will say also something in brief. So in the summer of 2020, which was mid-COVID time, was also more or less the start of my position here at KU Leuven. So through an interview process and everything, I selected Dharmjeet out of more than 100 PhD candidates that we had for that advertised position. So it was more candidates than on the later positions that I advertised. I don't know whether that was because of in COVID time, maybe people were more willing to go to academia rather than industry, or just because of the topic. I think it was a very interesting topic. Now, before Dharmjeet made his decision whether or not to accept this offer, he has to visit our campus in Brugge, because he knew Leuven, the Leuven campus from KU Leuven, because he did there part of the master. He also stayed there over summer for research, to continue some research project there. But so he came here, visited, looked around, and from that moment, I kind of knew he would not be like any other PhD researcher that I had supervised before in the UK. So he has a few characteristics. First, he knows very well what he wants and where he wants to get in his career, and also knows how to get there. I think this is something that was very remarkable with him in comparison to some other people that I supervised. Also, a small example of his kind of forward thinking is that in the first month or the first half year of his PhD, that he already took a training on how to write a postdoc fellowship application. So he also has, of course, a very high ambition, and we heard the number of papers he already has, the number of awards he achieved. For his career stage, I think that's quite impressive. So he also wrote his PhD fellowship application, which was successful on the first try, so immediately, so very good as well. For that application, there were still a lot of modifications in the last week before submitting, also for some reviews of papers. He was a bit last minute sometimes, but he also did show a lot of patience to get a high impact or a high result, and that was reflected in the review paper that he wrote. He said, if I do the effort of writing a review, I want it to be in a very good journal. So he looked at the 3 top journals for reviews, and he managed to get his review paper in Progress in Material Science, which is quite an impressive achievement as well. During his PhD, he also supervised quite a lot of master students. And so I can also give some quotes of the master students on him. So some examples are, Dharmjeet was prepared to help at every moment. I think also the research group members will confirm that. He taught me how to conduct research, so that's another master student who wrote this. Dharmjeet was a positive, motivating source and kept my head focused on the objective. And another quote that I wrote down from one of the master students is that Dharmjeet deserves tremendous recognition for his exceptional mentorship during this journey. So I think that's all very, very positive. Besides his PhD research, he got also active in other things like organizing and being the president of the doctoral working group and organizing activities for that. He also was part of a committee of the division of the Royal Society of Chemistry. So he looked also beyond the normal duties, let's say, of a PhD researcher. He also went to many international conferences, and of course that cost money, but he applied for also a lot of travel grants to support all these travels and presentations of his work. So he went to many countries to present his work, share his research findings, and also do a lot of networking. In addition, in the last year of his PhD, he also managed to get to conduct a research stay of 5 months at MIT. Also for that, he got money to support this research stay. So I hope with all this travel and visiting many countries and an institute, and that it helped him grow both as an academic researcher and as a person. So today is a day to celebrate Dharmjeet's success. It's also maybe a moment of reflection on the last years and to look at the future, a future of quite exciting possibilities. So I'm sure Dharmjeet will continue to make valuable contributions and to inspire others and push scientific boundaries. Congratulations.
Thank you very much for your kind words. I could not prepare a proper acknowledgement, and given the time we are already at and the very nice reception is waiting for us, I would not take much time, and I would start with thanking you, all of you, to come and attend my thesis in person, and also those people who are attending it online. So yeah, this PhD is a key milestone in my life, and this wouldn't be successful with the help of many people. And first and foremost, I would like to thank my family who gave me the upbringing, which filled me with so much confidence. So yeah. And then I would like to thank my supervisor, Professor Ville van de Hinstes. He has been a tremendous support, a mentor who also needs a super high amount of recognition because of her hard work and inspiring work she does at this campus. So a big thank you to her to have me in her group, and it has been a pleasure to work with her over 4 years. And yeah, I think there isn't enough word to appreciate her support to me. Apart from that, I would also like to thank my co-promoters, Professor Frederick Desplantre and Professor Paula Moldernas. They have been supporting me throughout all my research, and they have been always willing to help me with the comments and reviews on my work, and also whenever I needed some support in terms of infrastructure or resources, they have been always available to help me get them the way I want. And after that, I would like to thank all the jury members, starting with Professor Ruins, who took his time to be the president, or let's say, for being the president of this jury committee, and he did a great job. So thank you very much for your management and your time. And apart from that, Professor Anne Mignon and Professor Dr. Paul Lambert, he has been in my committee from the start and helping me through the revision and also suggestions on several parts of my PhD thesis. So thank you very much for that. Professor David Saveno, he has been helping me with so many experiments, providing me support in MTM in Leuven whenever I go meet his students or meet him. Always great to see him and talk to him. And yeah, Professor Ron Zevenhoven, thank you very much for coming from all the way from Finland and giving us the Meet the Jury seminar and also providing me valuable comments. It is much appreciated. And so I think I did not miss anybody. And then I would also like to thank Professor Wim Tillemans, who is not here, but of course he has been a great support to me in providing lots of resources and many other things at the campus, and it is always a pleasure to meet him and see him. The energy he has is a great inspiring, and he always motivates me whenever I see him, so it's a great pleasure to see him, and hopefully I will see him in 2 days when he comes to this campus for the next PhD defense. And with this, I would like to thank all the people at Campus Bruce. It was a pleasure to work with all of you, and having so many friends is great, and working with DWG and doing so many events, playing badminton or football or anything we do after the work or we meet, it has been great pleasure. I cannot take name of everybody, but you all have been great, and I think I have mentioned everything in the acknowledgement, so you can find out in my thesis and read it. And yeah, so I think I should wrap it up immediately, or we will miss the great reception. Yeah, What's next? I will be still around for a few months here to see you, and then I will try to find something. I don't know if better or not, but if I want to grow in my career, I think I should move on from here. That's the truth. So yeah, I'm here for some time to publish all the work I have done, because not all of them are published. So I will publish them, and then then try to find something which will suit my career better. Yeah. And there are so many friends and other people who have supported me throughout this journey, and I have mentioned all of them in the acknowledgement in my thesis, and you can find them out. So at last but not at the least, I would like to thank all the support members of KU Leuven in Campus Bruges or in Kortrijk in Leuven. They have been a great support, especially some of them, they made me feel at home much more than many colleagues. So it's really good to appreciate their effort, because they put a lot of effort to make the international people feel like at home. So I appreciate the effort by Ronnie, Machtel, and Yoke especially. They have been great. And also at the end, I would like to thank the FWO, who has provided me with many fellowship. I got successful in everything I applied with them, so there is no rejection. So and many travel grant and many research grant, and also my PhD fellowship. Now I have applied for the FWO postdoctoral fellowship in a very short time, and I think if it is successful, then I will have the track record of having everything successful with them. Thank you, FWO. Yeah, that was all. A nice reception is waiting, but before that, I would like to take a group photo. So please, everybody outside, we wait for a while to have a all-together photo with the all group, and also, of course, with the jury member as well. That would be appreciated. Thank you.